Hello everyone. So we started Green's theorem last time and we saw some examples. Now I want to move on to Stokes theorem. Stokes theorem. Um, so first, let's remind ourselves about the one-dimensional FTC and also what we saw for Green's theorem. So 1D FTC was saying that integral a to b f prime of x dx equals f of b minus f of a. And um, so also for Green's theorem, so these are the reminders. And for Green's theorem, we saw that integral f dot dr is same as integral curl of f dot k dA. So in that case, f was two-dimensional, and basically the normal vector to the surface, if our surface is xy plane, normal vector to the surface would have been just a vector in the z direction, which we denote with k. So f dot dr on some curve C is equal to curl of fkdA on R. So in this case, we have C as a boundary of R. And K is pointing towards positive Z direction. Now, can we generalize this to 3D? So now want to generalize to 3D. So our F previously was in the plane, so I had two components in I and J direction. Now it's a 3D vector field. So let F be a vector field. So this is the statement of Stokes' theorem, which is a generalization to 3D for Green's theorem. So Stokes' theorem. So let F be a vector field whose components have continuous partial derivatives on an open region containing S. And what is S? S is our surface, where S is an oriented, smooth surface with a positively oriented boundary. Positively oriented boundary. And let's call the boundary of S as rho S. Then what can we say? We can say integral f dot dr equals integral curl of f dot n ds. This one on the, so we call the boundary as rho s, and the surface we called it S. So where n ds is the oriented surface element. So because S is supposed to be the oriented surface, so N is basically pointing outward, perpendicular to the surface and pointing outward. So that's the vector N, and this quantity here so this quantity here that you can see, this is basically the flux. Flux of, but flux of not F, but flux of curl of F. Flux of curl of F. So Stokes theorem helps us to calculate flux of uh, curl of F, knowing or with just the information about the values of F on the boundary of S. So values of the F on the boundary is enough in order to calculate the flux of the curl on the whole surface. So this idea is similar to the idea that we had for FTC. When we look at the FTC, just as one-dimensional version. So the integral of derivative of f, so instead of curl, here we have derivative, can be calculated by only knowing the value of f on the boundary. Then you say f of b minus f of a. So see, when your interval is a to b, this is your set. So maybe you saw in analysis math 2 to 5 that the boundary of this set, this interval, are just the endpoints. So in this case, the boundary of a and b is equal to a and b. Just the boundary of the whole interval are just 2 points, and the endpoints a and b. So by only knowing the values of f on the boundary, f of a and f of b, we can calculate the integral of derivative of f on the whole interval. So FTC said that the integral of the derivative of the function on the whole interval is simply f of b minus f of a. So similarly here, to find the flux of f on the whole surface S, we just need to know the values of f on the boundary of S, denoted with rho S. Right. So now let's look at an example of Stokes theorem, a simple example where we can verify the theorem. We can calculate left-hand side and right-hand side and verify that they're equal. So let's look at an example. Let f of x and y and z equals minus y and x and 0. And S is the upper face of the unit disk. X squared plus y squared less than equal to 1, z equals 0. So this disk is on xy plane. So then boundary rho s would be the unit circle in xy plane oriented counterclockwise. So see, we said that rho s, the boundary of S, should be positively oriented. So what do we mean by positively oriented? Means that the orientation should follow the right-hand rule. So if you imagine the right-hand rule, so if we traverse basically or pass through the unit circle, counterclockwise, then the normal to the surface would point towards positive z direction. But if we move clockwise in order to still follow the right-hand rule, then your thumb basically, which is the direction of n, will point towards negative z direction. So as long as we follow the right-hand rule, so then the condition of positively oriented has been satisfied. So that means if we want to move counterclockwise, so see counterclockwise, clockwise, will correspond to the n vector of k, and clockwise corresponds to n vector of minus k. So here, let's assume we are basically covering the boundary counterclockwise. So then we'll have integral. So how can we parameterize? Then r of t will be cos t, sine t, and 0. And t belongs to 0 to 2 pi. So then we can calculate f dot dr. So how can we calculate f dot dr? The left-hand side of the Stokes theorem, f dot dr. So that means f of r of t dot r prime of t dt. And f of r of t will be minus sine t. So what was f? F is minus y. The first coordinate is minus y. And y is sine t. So minus sine t. So integral minus sine t. And second coordinate is x. X is cos t. And 0 dot r prime. R prime will be minus sine t, cos t, and 0 dt, 0 to 2 pi. And then if we do the dot product, we'll get sine squared plus cos squared, which is 1. So 0 to 2 pi, 1 dt. And this is t from 0 to 2 pi, which is 2 pi. Now, right-hand side of the Stokes theorem will give us curl of f dot n ds. So curl of f, let's calculate. So that means d f2 to dx so so let's calculate curl of f, determinant I j k d to dx, d to dy, d to dz, and f was minus y, x, and 0. So then this will be, the first coordinate will be 0, and then second coordinate will be also 0. Third coordinate will be 1 minus another minus 1. So plus 1 minus minus 1. K equals 2k. 2k. And then therefore right-hand side will be, so let's substitute back. Curl of f is 2k, n is k in the case of counterclockwise, as we mentioned earlier. So then we'll get integral 2k dot k ds on s, or this is integral 2 ds on s. So integral of 1 dA or ds is just the area. So this is 2 times area of R. And what was R? R was the unit disk. with radius 1, the unit disk. So area will be 2 times pi times 1 squared, or 2 pi. So 2 pi, we got 2 pi from both sides. So that means left-hand side equals right-hand side. And we verified the theorem for this simple example. So one thing I want to notice here, as I said, see, if you don't have the positive oriented boundary, then, for example, if you choose n as minus k, then right-hand side will be minus 2 pi, while left-hand side is 2 pi. Or if you cover the boundary clockwise, but still keep n as k, again, one side becomes minus 2 pi, the other side becomes 2 pi. So in order to remain consistent, we have to remain in the positive direction for boundary of S. So clockwise, if it's clockwise, keep it as n equals k. If it's counterclockwise, keep it as n equals k. If it's clockwise, you have to change n to minus k. Okay, I'm trying to see. It seems that my screen stopped sharing. But it doesn't say why. Okay, it seems it should be okay now, I think. All right, so let's look at the next example. So example, let f of x and y and z. So this time it calls a yz, xz, and xy. And S, let's assume it's the upper hemisphere of radius 1, centered at origin. And with z equals root 1 minus x squared minus y squared. So this is the equation of upper hemisphere, z equals square root 1 minus x squared minus y squared. Because obviously this implies z squared plus x squared plus y squared equals 1, which is the equation of the sphere. So z will be equal to plus minus root 1 minus x squared 1 minus y squared. And with positive sign, z equals root 1 minus x squared minus y squared. That would show the upper hemisphere, and z equals minus root 1 minus x squared minus y squared would be lower hemisphere. So we do have a surface, we have a vector field F, and boundary. What about boundary of S? So this would be the circle x squared plus y squared equals 1. So let's again verify Stokes theorem. So again, we can calculate the left-hand side. Left-hand side would be integral f dot dr on boundary of S. So if you parameterize boundary of S, would be cos t, again sine t, and 0, t belongs to 0 to 2 pi. So this is oriented again counterclockwise. So then f of r of t, so let's calculate this left-hand side. So therefore we can say integral f dot dr. How do we calculate? By calculating f of r of t dot r prime of t dt. So this is how we can calculate f dot dr. Now, f of r of t, what would it be? F of r of t, f of r of t would be, so f was, again, let's remind ourselves, this is f. First coordinate is yz, and yz, well, z is 0 in our curve. Look at the parametrization that we had. Parametrization here. So this is our r of t. So z value is 0, so yz becomes 0. Xz also becomes 0. But third coordinate is xy. Xy would be non-zero. X is cos t, y is sine t. So then this would be 0 and 0 and cos t sine t dot r prime of t. What would be r prime of t? R prime of t, again, let's look at r of t. R prime of t would be minus sine t and cos t and 0 dt, and then from 0 to 2 pi. So if you do the dot product, obviously you can see that we get 0 plus 0 plus 0. This dot product between these two are 0. In other words, they are perpendicular to each other. So this becomes integral 0 to pi of 0 dt, which is 0. So left-hand side becomes 0 in this case. What about the right-hand side? So we expect right-hand side to be also 0. So right-hand side. So for right-hand side of Stokes theorem, we need curl of f. So let's calculate curl of f. So this would be determinant ijk d to dx, del operator d to dx, d to dy, d to dz. And f was, if you remember, it was yz and xz and xy. So d to dx of, so d2, so if I delete row 1, column 1, d to dy of this is x, so this becomes x minus d to dz of this is also x I, and then delete row 2, column 2, minus y minus, again, another y, j plus, then we delete row 3, row 1, column 3. So then becomes z minus z, k, which is also 0 vector. So that means integral curl of f dot n ds on s would be double integral 0 dot n ds on s, which is 0. So therefore we show that left-hand side and right-hand side are both equal to 0. So this is another verification for Stokes theorem. All right, next example, let's look at z equals, or first let's look at our vector field. Vector field f equals f of x and y and z equals y and 0 and 0. And our surface S, upper half of paraboloid. So what's the equation of the paraboloid that you learned in Math 213? z equals 1 minus, we can look at 1 minus x squared minus y squared with x squared plus y squared less than equal to 1. So x squared plus y squared less than equal to 1 will guarantee that 1 minus x squared minus y squared will be non-negative, so z will be non-negative, and therefore that's why we are saying upper half of the parabolate. And then the boundary ds here will be x squared plus y squared equals 1. With z equals 0, and again we assume we are covering counterclockwise. Therefore, integral f dot dr here will be integral f of r of t dot r prime of t dt. So this will be, so this side will be easy to calculate. So this will be simply 0 to 2 pi, 0 to 2 pi, and then y value is sine t. F was y 0 and 0 dot r prime will be minus sine t cos t and 0 dt, and then this will be integral 0 to 2 pi minus sine squared t dt. Minus sine squared, very simple and standard integral. We can use a double angle, so minus 1 minus cos 2t divided by 2 dt. So this is minus pi minus 0. The answer becomes minus pi. So this is the, again, left-hand side. And now let's simplify the right-hand side. Right-hand side, we need curl of f. So curl of f, again, is easy to calculate. That will be determinant ijk d to dx, d to dy, d to dz. And then this will be y 0, 0. Then this is so first row, first column. If I delete, I'll get 0i. First row, second column, I'll get 0k minus 0j. 0j, and then first row, third column. So then minus 1k. So this is minus k. And now let's look at ds. So to calculate nds, the oriented oriented differential of the surface element, which requires us to calculate the normal vector. So this one, how do we calculate? So we know that n was so n, if you remember, was Rx cross product Ry, where R of x and y, let's say if it's x and y, and f of x and y. So this is the parametrization, surface parametrization, parametrization of a surface of the form z equals f of x and y. So if our surface is of the form z equals f of x and y, we can parameterize the surface as x and y and f of x and y. And then this will be, so then we look at this formula. So dr to dx, so that becomes 1 and 0, and df to dx. Cross product 0, 1, df to dy. So how do we calculate this cross product, determinant ijk 1, 0, df to dx, 0, 1, df to dy. Now if we calculate this, so this will be, so first row, first column, I delete it, and then we get minus df to dx, minus df to dx, minus df to dy, and 1. So in our case, what was f of x and y? In our case set was f of x and y, which was 1 minus x squared minus y squared. So if we plug in, we get 2x, 2y, and 1. 2x, 2y, and 1 will be our vector n. Therefore, we'll have integral double integral 2x, 2y. So curl of f was, this is the vector n. Curl of f is minus k, so minus k dot 2x, so 2x, and then let me write it as a minus x dot 2x k, because I wrote this one in the form of with coordinates. So the other one is minus k. Minus k means 0, 0, and minus 1. Let me also write it in this form. So 0, 0, and minus 1 dot, this one is 2x and 2y and 1 dA on the surface S. So this becomes integral minus 1 double integral minus 1 dA on the surface S. And we just need to calculate basically area, because integral of 1 dA same as the area. So how do we calculate the area in this case? So the easiest way to calculate the area is using polar coordinates in this case. So if you use polar coordinates, we can parameterize as x equals r cos theta, y equals r sine theta, and z will be z, or in this case, we just need the dA. So dA, for dA, we can write in terms of dx dy, or with polar coordinate, we can write as r dr d theta. So in this case, we'll have integral, so minus, there's a minus here, integral 0 to 2 pi, and then 0 to 1, r dr d theta, and r dr, so this becomes minus 2 pi times, this one will be r squared over 2 from 0 to 1. So this is minus 2 pi times 1/2, or just minus pi. Or we can just do minus, because the ds, the boundary of S, we mentioned earlier that it was just a unit disk. Here, unit disk, so it has the area of I r squared, or pi1 squared or just pi. So whether use that formula or just transferring to polar coordinates. So we'll see that this integral will be pi with the extra -1 in front becomes minus pi. So this is the right hand side, and left hand side we saw earlier that was also minus pi. So we showed that left hand side equals right hand side.